Let's start the topic properties and synthesis of alkenes. As you can see here, we have two molecules. One is from a marine sponge and another from algae. This compound contains 3 carbon-carbon double bonds, and this compound also contains carbon-carbon double bonds. Basically, these double bonds show that these are alkenes. Now if we look at the physical properties of alkenes, they are very similar to alkanes, but the difference is just the carbon-carbon double bond presence. They are non-polar. What is meant by a polar and a non-polar molecule? If I say that I have carbon bonded to an oxygen atom, let's say in an alcohol like this. So there's a difference in electronegativity value of carbon and oxygen. Therefore, carbon will have partial positive charge and oxygen will have a partial negative charge. So this compound will be a polar molecule where there are partial charges. But if we are talking about a molecule in which the atoms that are bonded are similar, carbon and carbon both are similar, so there is no difference in electronegativity value, therefore this compound will be nonpolar. Now, be it a carbon-carbon single bond or a double bond, the molecule will still remain nonpolar as long as the same atoms are binded together. And all polar solvents are for polar molecules solvation, which means that polar molecules dissolve in polar solvents and non-polar molecules, they are soluble in non-polar solvents, right? So it is written that they are soluble in non-polar solvents. From carbon 2 to carbon number 4, they are gases at room temperature, and as their molecular mass increases, they become liquids and solids above carbon number 4. Now if we talk about the cis-trans isomerism in alkenes, this is a type of isomerism seen where there is a carbon-carbon double bond, right? So let's just take a quick review of what it is. Right. So when we have same atoms binded on the same side, they will be cis. And if they're binded diagonally or in opposite sides, this is known as trans configuration. This only occurs when there is a carbon-carbon double bond. Let's move on to this thing. This shows that because of the presence of Hv, which is light, a molecule can exist in cis and trans form naturally. So this is a cis isomer and this is a trans isomer. If we consider this molecule over here, we see that this whole group and this whole group, they're lying on the same side. But over here, this group and this group, they're similar, but they're lying on the opposite sides. So this one is cis and this one is trans. Now if we look at the easy configuration, it is just an other type of configuration or another type of isomerism which we take into account when cis-trans is not possible, right? So we're saying that when cis-trans is not possible, it means that there is no similar group attached, right? In this molecule over here, you can see all four compounds or all 4 elements are different. In this compound here, we can see easy configuration and how it is observed. When high priority groups lie on opposite sides like this in diagonal, it is E configuration, and when high priority groups lie on the same side, it is known as Z configuration. Okay, and high priority group is the one which has higher molecular mass. Let's take this example over here. If I say, right, So if I have this example over here, we're taking this carbon double bond into account, right? So we're going to see this carbon first. We have bromine binded on one side and carbon atom bonded on other side. We're just going to look at the very first atom directly binded to that carbon. So the first atom is carbon. We're not going to consider this whole molecule and say that this molecule is bigger or this group is bigger. That's why we're going to consider this as the high priority. No, this is not high priority. Bromine has higher molecular mass than carbon, therefore it will be considered as high priority group. And if we look at this carbon over here, we have carbon directly binded and carbon directly binded. So it is a tie. We'll move on to the next element. The next one over here is carbon. The next one over here is also carbon. Again there is a tie. Then we'll move forward. Over here we have a carbon and a carbon, which means we'll take just one carbon, which means carbon is binded directly, and to this carbon atom oxygen is binded. When we're saying that we have oxygen binded directly to it and carbon binded directly to it, so we're going to compare oxygen and carbon. The same thing has been written over here. See, we'll consider carbon and oxygen in this case, and we'll say that oxygen has higher molecular mass, therefore oxygen has higher molecular mass than carbon. That is why it is taken as the high priority group. So we have high priority groups lying on the same sides like this, so it is known as the E configuration, Z configuration, right? On the same side we have it Z configuration. Now if we look at another example over here, this one, and I would say that we're going to consider this carbon atom, this one and this one. We're going to look at what groups are binded on both sides of these two carbon atoms. For this carbon atom, we have carbon over here and hydrogen over here. And for this carbon atom, we have chlorine over here and carbon over here. So, for this carbon atom, this is the high priority group because chlorine has higher molecular mass than carbon. And for this carbon atom over here, we have carbon as the high priority group because carbon has higher molecular mass than hydrogen. So again we have on the same side, this is known as the Z configuration. Let's move on to the relative stability of alkenes. Right. So relative stabilities depend on number of R groups attached. I'll say that if I have 4 R groups attached like this will be tetra substituted. This is tetra substituted, which means 4 molecules or 4 groups are attached. And if I say I have 3 R groups attached, 1, 2 and 3, and the 4th is hydrogen atom, this will be known as the tri-substituted alkene. Moving forward, we have di-substituted alkene. Now di-substituted can exist in 3 forms, right? One form is that both R groups are on the same side, are on the same carbon, right? And 2 hydrogen atoms are on the other carbon. Another possibility is that R groups are in transposition like this, and other 2 are hydrogen atoms. And the last possibility is that R groups are on different carbon atoms but in cis configuration like this, and hydrogen atoms binded like this, right? These all 3 are known as di-substituted because there are 2 R groups attached. Now if we go to the mono-substituted, we have only one R group right? All other are hydrogen. So the relative stability, how we're going to say which one is more stable. So tetra substituted is the most stable. I'll write it as 1. Tri substituted is lesser stable than tetra. Then in di, this one in which they're on the same carbon atom, this is more stable. Then trans is more stable than cis. Okay, and mono substituted is also less stable. Now if we look at cycloalkenes, they're very similar to cycloalkanes again, but the thing that we have to notice here is that all the cycloalkenes, there's a mistake, this is cycloalkene. So from carbon 3, 4 and 5, they only exist in cis form, which means, as you see here, let me zoom in, right? So if you see here, we have hydrogen binded like this and like this, hydrogen binded like this and this, hydrogen like this and this. They do not exist in trans configuration, they are only present in cis configuration. As we move from carbon number 6 onwards, we have trans configuration as well, like this. This image that you see here, cyclohexene, exists as a trans isomer as well. So this is the end of first part. We'll continue with the second part now.